So let's look at an example of using the ratio test. Here's a series from 0 to infinity, 3 to the n over n factorial. And the nice thing is there's nothing for us to check ahead of time, right? Ratio test says that can be any series. If the row comes out right, then we're good. So let's just jump into it, set up our limit. So rho is the absolute value of 3n plus 1 over n plus 1 factorial. That's our a sub n plus 1, right? You're just evaluating this expression at n plus 1 over the original form of that. And then usually the first step is going to be to flip it and get it, because you're going to have a fraction over a fraction typically. So what do you have? You have 3n plus 1 and an n factorial on top. And whoops, did it again. We're taking the limit, right? The limit as n goes to infinity of this. So the limit as n goes to infinity of, so when I flip it, 3 to the n plus 1, n factorial, 3 to the n plus 1 factorial. And right here, things simplify very nicely. When you have a ratio of exponentials like that and their index is only off by 1, then all you're going to be left with is 3, right? Because just use your rules of exponents. N plus 1 minus n is just 1. So you have 3 to the 1. So you just have a 3. And your factorials, this is 1 times 2 times 3 times 4 all the way up to n. This is the exact same thing, but it goes one factor more, right? It goes up to n, then n plus 1. So all the factors of n factorial cancel, leaving just the n plus 1. And that's actually one of the things to look for. We haven't seen much with factorials yet. And if you're a little bit confused about what happened here, I'm going to do a little factorial review here in just a second. But because factorials cancel so nicely like that when they're in a ratio, typically, not always, but typically factorials you'll end up doing a ratio test on. Because now, at this point, I guess this is still an absolute value, but nothing in here is negative, right? So I really could just drop the absolute value at that point. That limit is 0, which is less than 1. So our series, 3 to the n over n factorial, converges by ratio test. So yeah, two things actually work really great in ratio. Exponential stuff, because notice that just became a constant, and factorial. So I use this as an example because it's got the two things that work great in ratio. Now, if it's just an exponential by itself, then it's a geometric series. But if it's got that and some other stuff, ratio test might be something to consider. So we haven't seen much in the way of factorials previously because factorials only exist at the natural numbers. So when we were doing integration and differentiation in Calc 1, we never saw factorials. So this is kind of new. You may have seen factorials a little bit in algebra, but I do want to just do a quick review of factorials if you're rusty, because we are going to start seeing them a lot now. So by definition, we define 0 factorial to be 1, and then every factorial after that is the previous factorial times that next number. So that's the definition of factorial. So it's a recursive definition. You can get every factorial from the previous factorial. So what does that, in practical terms, what does that mean the factorials look like? So if 0 factorial, 0 factorial is 1 by definition. then by that recursive definition, 1 factorial should be 0 factorial times 1. So it also is 1. 2 factorial should be 1 factorial times 2, or 1 times 2. 3 factorial is 2 factorial times 3. So 1 times 2 times 3. And now you kind of see what's happening, right? 4 factorial, because it's the previous one, then times 4, you get this pattern of the product of all the natural numbers up to that number. The only one that you really can't say that about is 0 factorial, since it's not a natural number. And so on. And these numbers grow really fast. If you start computing these out, these actually grow faster than exponentials, which exponentials are the fastest thing we've seen so far. These numbers grow even faster. And so you could keep going in this fashion. So let's revisit this little simplification I did here. Why did that come out to be just n plus 1? Well, maybe if we write this out in a little bit of detail. So when you have a ratio of factorials like that, there's 2 ways you could think of it. By definition, n plus 1 factorial is n factorial times n plus 1. So those 2 factorials cancel, and you're left with just 1 over n plus 1. Or if you just write it out in sort of this fashion where you're writing out the actual product, the top is the product of every natural number up to n, while the bottom is the product of every natural number up to n plus 1. So this has 1 times 2 times 3 all the way up to n. This has 1 times 2 times 3 all the way up to n, and then 1 more. So all of those lesser factors are going to cancel. So you're going to see this sort of simplification a lot coming up because of ratio tests. And we're just going to see factorials in general coming up because they play a big role in the Taylor series that we're headed to. So yeah, make sure if you are uncomfortable with any of this factorial stuff that you go back and review factorials. We'll be seeing plenty of them here for the next few sections.